Section 3.7 is a topic called related rates. And the related rates idea is going to take us right back into something that we did earlier in Chapter 2 called implicit differentiation. Do you remember that? All right, so I'll show you how that works. It's done a little differently than we did it in that particular time, and for a different reason, but the process is similar. So to start with, guidelines for solving related rates problems. Just like in the last section with optimization, we're going to draw a picture if it's appropriate to do so. Second thing is we're going to set up an equation that relates the related quantities, relating all the relevant quantities. The third one was what I sort of hit on just a minute ago, is that we're going to be working with implicit differentiation. The difference between this and what we did before is that this implicit differentiation is related to time. So every time we do it, we're going to do it related to time now instead of related to the other variable in the equation. That's different. Fourth thing to take a look at doing is to substitute in the values that we know and the derivatives that we know. And the last thing is to solve for the rate that we're trying to find. Okay, you guys ready? I have 3 examples to show you, and this is what I was changing at the last minute last night before I posted these, was the order in which we did these. All right, so the first example that I'm going to show you, we're not, in fact, in all the examples that I'm going to show you, we're not given a picture. We have to draw the picture that creates the relationship. This one says, a fish is reeled in at a rate of 1 feet per second from a point 10 feet above the water. So let's just stop there and draw the image of what that's describing. We've got water. So we're going to start there. So here's my water. It's blue and everything. Look at that. And we are going to be 10 feet above the water. So I'm going to sort of draw us as though we're sitting, I don't know, in a boat or on a dock, at a shore, something like that, where the fishing pole is 10 feet above where the water is. Okay, so the fishing pole straight down is 10 feet. Are you guys with me so far? This is 10 feet. And the fishing pole has a line attached to it. I'll draw it in red. And somewhere out here is the fish in the lake. And we are trying to pull this fish in. Now notice as we pull the fish in, what happens is the fish doesn't go up this line, right? That's not what happens practically speaking. What happens is that this line actually moves in closer to the vertical line that we've got. So what's actually going to happen is that the angle is going to be changing, and this is the angle of elevation. And that's something you should have learned in trig, the angle of elevation. So the angle that this is talking about is elevation from the water up to the top of where our fishing pole is. Now notice the 10 feet does not change ever, right? But the length of this red line is going to change, and the value for the angle is going to change. Those things will change depending on how, at what point in time we look at them at. Okay, so let's write down some information. This is the overall picture of what we know, and let's give a letter name, a variable name, to the quantity that changes that red line. What do you want to call that red value? You want to call it x? Okay. So this x is the length of my fishing line. Now at some point the length of the fishing line, it actually says, is going to be 25 feet, but that's not going to be all the time. Just at one point in time it's going to be 25 feet. So let's take a look at what we know and what we don't know about this relationship. So first of all, let's just look at the pieces in the picture and tell me, what relationship do you know that relates the 10, the x, and the theta to one another? It is a sine function. Sine of theta equals 10 over x. Okay, does that make sense so far? We've put in the piece that never changes, the 10. We're not putting in the 25 because that 25 is not always going to be the length for x. It just is at one point in time, and we will do the 25 in for x, but not until the very end. Okay? But the 10 we can put in right now because it never changes. So if some piece of the information never changes, you're allowed to go ahead and evaluate that in the beginning, but not if it's a changing value. All right, so let's actually write down some of the things that we know at the end. We actually know at the end, I've already said this, that the x value is going to be 25 feet. We also know at the very end that a certain rate. It says that we have the fishing pole is pulling this in at a rate of 1 feet per second, right? That's how quickly that this red value, this red length, is changing at 1 feet per second. So we're going to write it like a rate. A rate is written as a distance over time, or somehow something changing over time. And that's what this part over here talked about, is that we're going to implicitly differentiate with respect to time. So the quantity, that we actually know here is that dx dt, that is how x is changing with respect to time, is -1 feet per second. Why in the world is it -1?
Because you're losing a per second.
Right, we're reeling the fish in. That line is getting shorter. Make sense? Okay. What are we asked to find? This is what we know. What are we wanting to find in this problem? Rate. The rate of what?
Angle.
The angle. It's how the angle's changing. So we're going to write that as d theta dt. That is how the angle is changing, d theta, with respect to time, dt. That's what we're looking for. So this is sort of the piece of that we're trying to find. Let me put some information in here. Blocks this off. All right. So this is the equation that we're going to be working with, the sine theta equals 10 over x. And I'm going to write it as 10x to the -1. Because what we're wanting to do is we're wanting to differentiate this with respect to time. That was step 3 or whatever over here, right? Differentiate implicitly with respect to time. All right, so what is the derivative of sine? Cosine. So the derivative of sine theta is cosine theta. But we're doing this implicitly, which means that anytime I take the derivative of the variable, I'm going to write times the rate that that variable is changing at. So that's d theta dt. When we were doing implicit differentiation, that's when we would have written y prime. Do you remember doing that? We're doing the same thing here. We're just going to write it as a ratio because we want to keep remembering that we're doing this with respect to time. All right, so what's the derivative of 10x to the -1? And then I need to write with respect to time, so it's dx dt. All right, so I mean, we can clean this up a little bit, not a lot, but this is cosine theta d theta dt equals -10 over x squared dx dt. So not in theory, but in practice at this point, we're actually at step number 4. What does step number 4 say? What do I need to do? Substitute in the values that we know. And we know some of them, right? I wrote them down over here so that we sort of have them when we're ready for them. We know that x is 25, so I can put the 25 squared on bottom. Okay. I know that dx dt is -1, so I can put the -1 over here for dx dt. I know I'm looking for d theta dt, so that's fine. But there's something missing. Theta. I still don't have a value for theta, but I can find one. So let me pause for a second and get this copied to the next screen. So some more space to work. Okay, so like we said, we've got x equals 25, dx dt equals -1. And we need to figure out what is theta going to be so that we can actually solve for the d theta dt. Well, we have a relationship that relates theta and x together, don't we? It said sine of theta equals 10 over x. So at a given point in time, there is a distinguishable angle measurement that we can find. So we actually are going to solve for theta when the time, or at the point when x is actually 25. So we're going to plug in the 25 and we're going to solve for theta. How are we going to do that? Inverse sine, and that's that little negative one looking sort of like an exponent. Inverse sine, and your calculator will be able to do that for us. Okay, word to the wise, it should already be done, but make sure you're in radians. All of your derivatives for sines and cosines and all the trig derivatives are based on using radian angle measurements. Okay, so that's why this is important. We need to find out what is the theta value. And let's go with 6 decimal places for now, just to keep things without having any error in them. We'll go with 6, should be sufficient. What is the inverse sine of 10 over 25? Okay. Did anyone else's calculator give them the same thing? Excellent. Alrighty, so we actually can use that information up in our formula now. So we've got the cosine of 0.411517 d theta dt equals negative 10 over 25 squared times negative 1. So on the right, I have 10 over 625. And then, actually, I'm going to divide that after I find a decimal for it by the cosine of 0.411517. And because of the types of angle measurements that we're working with and so forth, let's go ahead and keep, let's say, 4 decimal places for our solution. So take 10 over 625, press enter, and then divide that by the cosine of 0.411517. What do you get?
0.07. We're doing 4 decimal places?
0.07 what?
Are we doing 4?
We'll go 4, yeah.
175.
Okay, so is it 7 or is it 8 at the end?
0.17.
Like this?
175. Yeah.
175. Okay, I misheard. I'm sorry. Yes, 0.175. We need to take a look here at what the units should be. And this is another reason why this notation is really nice, is because if you look at the notation, you can figure out the units. How is theta being measured? Radians. T is being measured in time. So this is radians per second, or minute, or however they've got it measured. They've got second, yeah. So this is changing at a rate of 0.0175 radians per second. So far, so good? Okay. This is a nice one to sort of bring in your trig to think about. You've got a couple of them as your homework. They're going to have triangles and trig and stuff like that in them, okay? So thinking about those trig relationships. Let's do another one, not trig. A spherical balloon is inflated with gas at a rate of 800 cubic centimeters per minute. How fast is the radius of the balloon increasing when the radius is 30 centimeters? Where do I start? Draw a balloon. That's right. We're going to draw a spherical balloon. So we're going to start with a circle. I'm going to make mine a red balloon. And I have technology advantage on the circle there. All right, here's my circle. And it's actually asking something, or giving me some information about cubic centimeters per minute. What kind of a relationship is that referring to in terms of my balloon? Do you know?
Volume.
It's volume, because it's cubed, right? A cubic measurement is in terms of volume. So this is one of those questions, and there may be a couple others in your homework where you might have to go back and look up a formula if you don't remember it. Do you remember how to find the volume of a sphere? Close. That would be the area. I'm done. Pi r cubed. There's a 4/3 missing in that. I'm sorry. 4/3 pi r cubed. I got ahead of myself when you guys are saying pi. 4/3 pi r cubed. You can Google that easy, right? It's probably in the front flap of your textbook if you want to be real honest. Usually the fronts and back flaps of your textbook will have formulas for some of the basic shapes like this too. All right, so this is 4/3 pi r cubed. Notice there's only one variable on the left, v, and there's only one variable on the right, r. So we only have two things that are changing here. It's the radius and the volume. Okay, so let's write down what we are given, what we know, and what we're asked to find. So this 800 cubic centimeters per minute, what quantity is that? Close. It's the rate of the volume. It's dV dt. And it's increasing, so it's positive, right? Because the balloon is being aired up, not being deflated. The other piece of information that we're given, again, it's not constant, that is, it's not always 30 centimeters, but there at some point in time it's going to be 30 centimeters. What is the 30 centimeters? The radius. And what are we asked to find? We're asked to find dr dt, that is, how is the radius changing? All right, so we're going to take this volume equation and we're going to do what? What are we going to do? Take a derivative. Okay, so we've got v equals 4/3 pi r cubed. So what would the derivative of v be? dv dt. It's normally why we write v prime, right? But v prime is a derivative notation. One of the derivative notation methods is to write that as dv dt, because our measurements here, or our derivatives, are being taken with respect to time, not with respect to radius. All right, so the 4/3 is going to stay. What's going to happen to the pi r cubed? What is all got? What are we going to get?
3 pi r 3r squared dr.
Okay, so I'm going to have the 4. I'm sorry, the 4/3. I'm going to have the pi, and then the r cubed is going to become 3r squared. What's missing, Ben? Yes. Okay, again, it's implicit differentiation, so anytime you encounter a variable, you're going to have a rate beside it. So if you took the derivative of r, you're going to have dr dt next to it. If you took a variable and your variable is x, you're going to have a dx dt. If the variable is y, it's dy dt. It's always going to be there. All right, this simplifies to start with. Dv dt equals 4 pi r squared dr dt. And this one's not too bad because I actually have all these pieces, don't I? Let's see, dv dt is 800. The r is 30. And the only thing I don't know is dr dt, which is what I was looking for. So this one's actually a little bit cleaner than the last one, except that you didn't know the formula for the volume of a sphere. So. Details, details. I know. All right, so this is 800 equals 4 pi. The r is 30, so it's 30 squared dr dt. So I have 800 equals 4 pi times 900. And if we solve this, we're actually going to find that dr dt is that 800 divided by 3600 pi. You can enter it just like that if you want. You could also recognize that the zeros are going to cancel, so you could enter this as some version of 8 over 36 pi. Yeah, and that would, the 8 and the 36 can't simplify as well. But dr dt then is what we're actually looking for, and we're looking for it. We'll go with 4 decimals since we used 4 decimals in the last one. That seemed to work pretty well. What is the 4 decimal value of dr dt?
0.0707.
Okay, 0707. What are my units going to be on the problem? Okay, so we first have to do the units on the radius. What are the units on the radius? Centimeters. And then the time, was it in minutes on this one? So this would be centimeters per minute. So the balloon's radius is increasing 0.0707 centimeters per minute. Okay, we okay? Kind of tired. Okay, well, the next problem will wear you out then.
Marvelous.
So when I first created the lesson, this next problem was the first problem, and I decided that was probably the bad choice. So here is our last example, and you're going to have one or two of them that have the same feel to it in your homework. Oil is spilling. It's not good, right? I thought maybe we could change it from oil to something else, but then we're going to run into a problem because if you did water, it wouldn't have a thickness of 1/8. So I left it. The oil spills out of a tanker at a rate of 90 gallons per minute. So can you picture what's happening?
It's spilling
Are we
fast.
Right.
certifying ourselves to work for BP?
No. We're not going to work for anybody. We're going to try and figure out the problem. That's all we're going to do. Okay? All right, 90 gallons per minute. The oil spreads out in a circle, and the circle has a thickness of 1/8 because oil's thick, right? So that's why it's got a thickness to it. If we were talking about water, it wouldn't really do that. Although we could talk about water spreading out, like on pavement, it evaporates into it, and it does sort of spread out in a circular pattern. If you've ever worked with any kind of a liquid like that, you've seen that happen before. This one has a thickness of 1/8. It says to determine the rate at which the radius of the spill is increasing when the radius approaches 100 feet. That's a really big puddle of oil, right? We got to start with a picture, right, Blaine? What's this picture going to look like?
A circle.
A circle. It's actually not quite going to look like a circle, though,
There's a 1/8.
because there's a 1/8 height. So what's the picture really going to be?
Small.
A very small cylinder. Can you guys picture it? It's like a circle, but it's got width to it, height to it. So that's a cylinder, like a toilet paper roll, but really short. Okay? So we've got a cylinder that we're looking at here with a very tiny height to it. Something like this, in theory. Here it is. So here's my sort of not so great picture, but you can visualize anyway. So the first thing you've got to ask yourself is,
What's the equation for that volume of the cylinder?
that's exactly right. What's the equation for the volume of a
That's
cylinder?
a very good question.
It's a very good question to ask. And I'm going to be very helpful and tell you what it is. So the volume is pi r squared h. What it actually is it's the area of a circle, which is pi r squared, times the height. Okay, so that's actually not as complicated as the spherical one. It actually has pieces that we see where they come from. All right, so thinking about this then, there is a problem here that didn't happen on the last, there's a couple problems that didn't happen on the last example.
We have more than 2 variables.
We've got more than 2 variables. That's the first noticeable problem, right? I've got an r squared and I've got an h. And it sort of looks like I have 2 variables, but I actually don't. Do you know why?
Don't you have both of those variables in the?
Oh, the height doesn't change.
The height, Taylor, yes and no. I do know the height, and I know the radius, but I know the radius at one point in time, which means the radius is changing. However, the height doesn't. The thickness, the height of this cylinder, so to speak, is a constant 1/8. So I don't really have 2 variables here. So that's the first thing to sort of make amends to the fact that this is pi r squared times 1/8. I don't really need an h in the problem. It's part of the equation, but it isn't changing. So I'm not going to have any variable there for that. All right, so let's write down what we do know then. We know some pieces of, what is this 90 business? Do you know?
All d or dt.
That's dV/dt. It's 90 gallons per what? Minute. And then Taylor, you mentioned I actually know the radius at the specific point in time, which is the 100 feet. And we are looking for, right, we need to find dr dt. Now, there is an innate problem in this problem. There's a problem in the problem. Do you see the problem? I'm going to go back to the last 2 examples and make mention of something that you probably weren't aware of happening that's different here. Notice on this particular problem Our x was measured in feet. dx dt is feet per second. My answer at the end of here is in something per second. Next problem. I'm being measured, this 800 is in cubic centimeters per minute. My radius is given in centimeters. My answer at the end ends up being in centimeters per minute. What's different here?
We have gallons per minute, and then we have feet.
And you have inches.
We have gallons, minutes, and we have feet.
Somebody
We need
was
a
mean.
comment.
Somebody was mean. And so you know what? Here's what I had to do last night when I was looking at this is I had to Google and figure out how to make amends with that. Because something about that's weird, right? Well, here's the deal. This is what I found out when I Googled. I found out that when you take a gallon, that it is equal to 231 cubic inches. So I'm going to show you how we use that in a minute. That puts things in inches anyway. That's better than in gallons because I can measure in inches. And what could I do to this feet?
Change it to
I could also change it to inches because I also know that 1 foot is equal to 12 inches. So the first thing I have to do on this problem is I've got to get the units to match up. I cannot work this problem with all the units being different. And in reality, there's a lot of that happens in real life. The units just don't match up, and the first thing you got to do is get them to match up. So the first thing I need to do is I need to change all of these to have matching units. All right, so the dV dt started out as 90 gallons, was it per minute?
Yes.
Okay. And what I want to do is I want to write this, and you guys have done some chemistry, I know, so this kind of a conversion shouldn't look foreign to you. We're going to, excuse me, we're going to write this with a ratio between the quantities that are the same. Over here, we found out that 1 gallon is the same thing as 231 cubic inches. So I actually can write this as 1 gallon on the bottom of a fraction, and then the 231 cubic inches on the top, because they're equal to one another. This is equivalent to multiplying by a fraction that's the value 1, because the value on top is equivalent, different way of writing it, to the value on bottom. And then if you see this, the gallons cancel, and I'm left with cubic inches per minute. Okay? So what is 90 times 231?
20,790.
Cubic inches per minute. And let's also, while we're at it, go ahead and find out what the R would be. We had 100 feet, right? And we can set up the same kind of a cross, or same kind of a fraction multiplication with this one. This is 1 foot is equal to 12 inches. And we can notice that the feet cancel. So 12 times 100 is 1,200 inches. Now I actually have everything all in the same units, and it's usable information. Now, let me just make one real quick comment that we haven't done any calculus.
Yay!
The calculus on this particular problem is not the difficult part, okay? So our formula was that volume equals, I'm going to write the 1/8 in front, 1/8 pi r squared. So we need to do what? Take the derivative. So what is the derivative? What's the left-hand side going to say? dV dt. What is the right-hand side going to say?
1/8 pi times 2r dr dt.
Okay. Is everybody good with that? And then we know all those values. Let me go ahead and simplify one little bit before we start. This is the same thing as pi over 4, right? Because I've got 2 times pi times 8, 1/8. And then I've got my r, and then dr dt. We know all these quantities now. All of them except for the the dr dt, which we're looking for. So the dV dt is 800. Started out 800, I'm sorry. That was the last problem. 20,790. Get the numbers right. Pi over 4. My radius is 1,200. And then dr dt is what I'm looking for. This will simplify to 300 if you'd like. So dr dt is 20790. divided by 300 times pi. Make sure that the 300 and pi are multiplied together before you do the division. Okay. What do I get for drdt?
22.06.
Say it again for me.
22.06.
22.06 inches
Per minute.
per minute. And how did we get inches per minute, Mandy?
Well, because we moved it all to inches and then it was already in, the time was always in minutes.
Right, we can actually look back at the ratio that we've got on the left-hand side. It's got inches for the radius on top, you know, those are the measurements, and then time is in minutes on bottom. I'm fine in general with 2 decimal places, that works for me. The reason we used 4 decimal places on the last 2 problems was because those quantities were very, very small. So I'm not gonna be super duper picky except to say that give me some length here in what your answers are going to be, okay, at least a little bit.